Hi guys, Professor Simmons here. Um, so we're about to get into projectile motion. Um, and before we do that, we need to take a little bit and talk about vectors with a little more rigor. So far we haven't really talked about them in a quantitative way. So we're going to do that now. And for some, I think this will probably be, you know, just review. You've seen this before. That's okay. But for others, you may not be as comfortable with this. So I want to show you some things once anyway, just so we can help kind of get everybody on the same page. So vectors. So qualitatively, we know that it's a number that has a magnitude and direction. So, and we know that velocity and acceleration and displacement are all vectors. And we probably also know that you can look at vectors graphically. So you can add vectors together. The simplest case being, if you have two vectors that are pointed in the same direction, if you add them together, you would have a vector that has the length of both. Or you could have vectors that, so here, let me just give you a few examples. You could have vectors where they're not pointed in the same direction. So a real simple case would be if they're pointed, if they're anti-parallel. Then when you add these together, these sort of cancel. So you'd end up, the result of adding these two vectors would be a little shorter vector. And then, of course, what we're really interested in is if things are at angles to each other. So if you want to add a vector that's pointed like this with a vector that's pointed like this, what you can do that graphically by simply where one vector ends, you can start the next one, and the resultant vector will start where you start and end where the second vector ends. So it would go like, it's tough to draw diagonally here, go like that. So if this was v1 and this is v2, and I should really be careful. So our notation, we use a little arrow over the top of the symbol to indicate that it's a vector. So I'll try to do that, but invariably I'll forget sometimes. These are all examples of vectors. And you can tell that you don't have to get very complicated before this is basically useless in a quantitative way. It's just too hard to draw things well enough to do any sort of actual computation with this. But where this is really useful, it's helpful for keeping track, but it's not very useful for figuring out actual numbers. So in order to use this for calculations, for solving problems, etc., I'll introduce you to a couple ideas that are really useful. So one is vector decomposition. So I suspect if you've messed with vectors at all, you've probably seen a picture that looks like this. So suppose we have some vector, draw a coordinate system where this vector is starting at the origin. This is the x-axis. Actually, let me draw it like this. I don't want you to think the coordinate system is also vectors, but we have an x and a y-axis, and we indicate this as being at some angle above the x-axis. And what we can do is we can break this vector into its x and y pieces. So in other words, there's going to be this projection of the vector, this amount of the vector is in the x direction, and this is in the y. So suppose this was some velocity vector or something v. We might call this vx and vy. And this process of breaking the vector up is often called vector decomposition. This is a skill that you're going to need to be totally fluent with. You're going to use this a lot. We're going to use this in the immediate future when we talk about projectiles. You need to know the horizontal velocity and the vertical velocities of your projectile. And to do that, to break this up, we need to know the relationships between the components and their trig functions. So I suspect you've seen this before, but I want to show you in gory detail once. So recall your trig functions. Sine theta is going to be what? That'll be Vy over V. When I say V, I mean just the length of V. So I'll put a couple bars there to indicate the magnitude. So what this means is if you want Vy, you can get that by multiplying sine theta times V. And actually, let me just write it the other way around. This is how we usually write it. Okay, so that's the y component. Similarly, you know that you should know that cosine theta would be Vx over V. And so if we wanted Vx, we would just do V cosine theta. Okay, so you'll know this. If you don't know this like the back of your hand, you're going to, because you're going to use this all the time. Now, I want to put in red here a word of caution. Put a little to emphasize. You want to be really careful about this and be mindful of the context. So what I mean is that it's like many students, they're really accustomed to, oh yeah, x is associated with cosine and y is associated with sine. So the thing that I want you to be careful about is it depends on how your angle is given to you. If you get some question where, oh, actually theta, or let's call it alpha, say, is up here, when you go to break this into x and y components, your trig functions would be reversed, and that could lead you astray if you just rely on memorizing x is associated with cosine, y associated with sine, etc. So I'm just going to put here, depends on the context, and encourage you to always draw a picture to help you straighten out which angle is which. And be careful that when you're examining a problem, that it's not just given to you. If it be careful if it's given to you in a way that's not what you're accustomed to. So while we're talking about vector decomposition, this is actually a really good time to talk about, in addition, how do we indicate vectors that are along the coordinate directions in a rigorous way. And we do this using this idea of unit vectors. And you may or may not have seen this, but if we imagine, let's imagine our coordinate system 3D. There's different ways to do this, or I should say different conventions. And the convention that we're going to use and that your textbook uses is to use I, j, and k hat to indicate x, y, and z respectively. So a unit vector is a vector along one of your coordinate axes. And it has a length of 1. And you can think of this as sort of a label that's telling you the direction that something is going. And we'll go into more mathematical detail with this when we talk about different kinds of vector multiplication. Depending on where you're in calc, you may have dealt with the dot product or the cross product. And to do those operations, you need to be able to work with these unit vectors. But for our purposes now, just think of it as a label that tells you the direction that something's going. And it's a special vector that has a length of 1. So you can think of this as being centered at the at the origin, these little vectors. And the convention is I hat, j hat, and k hat. So the little hat on the vector is to indicate that it's a unit vector. So just to be really explicit here, the x direction we indicate as I hat, the y direction is j hat, and the z direction we indicate with k hat. So if I want my description of my vector decomposition up here to be a little more rigorous, really what I should do is the y component would be v sine theta, and that's in the j hat direction. And the x piece would be v cosine theta, and that's along the I hat direction. And this just gives a little more vigor, so or rigor, I should say. So this Vx is just a magnitude, but as I've written it now, it's a vector. Okay. I think that's all I wanted to mention about that. Like I said, we'll get into more mathematical detail when we talk about different kinds of vector multiplication. But so we talked about breaking something up, vector decomposition. The other thing that I should show you an example or two for is adding vectors. So this is kind of the other skill that you're going to need to be able to use to really exercise, because it appears again and again in physics as well as your other courses. I'm sure you need to be able to sum vectors. So let me show you a couple examples. Kind of a simple example, sort of a classic example, is you imagine you have like a river or something, and the river is flowing. There's a current, okay? And you imagine a person that's trying to swim across the river. And what's going to happen is while they're swimming across, they're also going to be moving with the current. And so if we think of this as, this could be a displacement or something. And then this could be, how far they drift. Let me just use letters to indicate this. And the resultant displacement is going to be the diagonal of those. So, and this is kind of the special case when these things are perpendicular. In this case, it's easier to analyze. So if you want to find the magnitude um, of this resultant vector, you would use the Pythagorean theorem. So you could show that the length of that c would just be square root of a squared plus b squared. And then along these lines, if you wanted to figure out, what angle this was at relative to the x-axis, that angle is related by tangent. So tangent theta is b over a. So you could use that relationship to figure out the angle. This has multiple applications. These could be velocities or displacements or whatever. It's just sort of, this is sort of the special simple case where you have things that are at right angles. This will appear again and again. Let me show you a little more complicated example. Now, I'll try a little harder to draw this, but I want us to imagine adding two different vectors. So we'll have one like this. Have some angle off the y-axis alpha. And this is vector A, where the length of A is going to be 3. And the other vector is going to be pointed like this. And this is going to be theta 2. And the length of B here is going to be 7. And this theta 2 is going to be 35 degrees. So we're going to do an example with some actual numbers here. So we can approach this graphically. You'll see that I'm sure I'll have trouble drawing this, but what you would do is you just put the head of one vector, stick the tail of the next on. So we're adding these vectors again. So I can try and do this graphically. So roughly, the resultant vector would be something like this. Okay. Now, as I've been emphasizing already, it's really difficult to be very quantitative with just your picture, but it does give you a feel for, okay, it's going to be pointing sort of to the right, maybe down and down. And so what you can then do is you can be really methodical with breaking things into components and adding the components and then finding the magnitude and direction of the resulting vector. So that would be my piece of advice, would be really methodical. So let's look at the x components first. Okay. So if we look at A, if we want the x piece of A, now notice I put this off the y-axis intentionally just to draw your attention to the fact that if you want the x piece of this, that would be sine alpha. But what I would recommend is do yourself a favor and just redraw this off the x-axis. So you have theta. Now this has to be, if this is 50, then this would have to be 40 degrees. You're free to put things into what you're more familiar with. So if we do that, the a x piece would just be a cosine theta. The bx piece would be b cosine theta 2. Okay, let's look at the y components. So the y components, if we want a y, that's just going to be a sine theta. The by would be b sine theta 2. Now, this brings up something that I want to draw your attention to. Is this exactly right? Well, we have to be careful about the signs when we're talking about an angle that's below the x-axis. So you can tell just from your picture that you know that the y component of this is going to be negative. So there's two ways you can deal with this. You can either say that this is negative b sine theta 2, where you're indicating you're working with the assumption that that angle, that number is positive. Or you could specify this as b sine and make sure that this angle is negative. I don't care what you do, but be consistent about it. And the other thing I would mention is that this is another argument for why it's always a good idea to draw yourself a picture. So if you have the picture, you can tell, oh, I'm looking at this. I know the angle has to be, or that component has to be negative. Okay, so I'll just put a note here. Be careful about signs. Okay. So then the next thing we do, we want to add the components together to find r. So the x pieces, now since these are in the same direction, it's simple. We just add the chunks together. We'll put in our actual numbers here. 3 cosine of 40 degrees. You know, another common error that I would mention is that be mindful of if you're working in degrees or radians. That can cause kind of mysterious errors sometimes if you're less comfortable or familiar with that distinction. This is 0.03. Let's add up the y pieces. I'm just going to use the convention that we're assuming that that theta 2 is positive, but we're recognizing that we're subtracting it. Put in our numbers. We get negative 2.09. And then if we want to find, the total magnitude of this, we would use our Pythagorean theorem. Now, I would point out, you notice how I'm carrying through all these digits. You don't want to inadvertently round your answer before you complete your calculation. But we will make sure that our result has the right number of digits. So our numbers were given with 2 digits, so our result will be rounded to 2 digits. So the length of r is 8.3. And then the other piece of information that we could get would be the angle. So what angle is that at? So my picture is not super good here, but we know that this thing is, it has a magnitude of 8.3. The other thing that we're trying to find is the angle. So let me call that theta r. And like I described above, we can get that from the tangent. So we would take the arctangent of the y piece or the x piece, and we would find that this is about negative 15 degrees. So this is 15 degrees, and R has a magnitude of 8.3. So this gives you an example in kind of gory detail of adding vectors. Those vectors are, they're not perpendicular to each other. So we break them into x and y components and sort of methodically keep track of the x and y components, add the components, and then find the resultant magnitude and direction of that vector. So this is a mathematical skill that you need to be, um, you know, totally good with. It's going to appear again and again in your engineering education. So hopefully this helps.